crystallize on this borderline. This film of salts can be broken down into small particles and fall into the heated gas phase. Like shown on this animation, and on this animation too. It's metal rain, because the particles in the heated vapor under the action of laser radiation, they are heating there, melting there, and reacting there, and forming small balls, small drops of liquid metal. And by this way, those particles form of nanocoatings and homogeneous monolayers of nanoparticles. Okay. And there are many tracks consisting entirely of sprayed nanoparticles. For example, this is one of them. It's a track formed by LCLD with around 56-55 micrometers and with very homogeneous surface consisting of spheric nanoparticles, nanoballs, with diameter around 120 and 140 nanometers. So after that we cracked the sample to investigate it more attentively, and after that we can see the cross-sectional view. We will see cross-sectional view of this track with, and we can measure the thickness. It's around 1-2 micrometers. So this is a really thin film with hills and valleys on the surface. And also we can see on the cross-sectional view, we can see that there is two types of topology in this track. External topology, and on the top layer we see the smooth layer of nanoparticles, nanoballs, very homogeneous layer. And inside of that we can see the chaotic topology, a random topology with many defects and empty spaces inside. Okay, to get additional evidence, of our mechanism, metal rain mechanism, we removed from one of the part of this track, from one of the places of this track, we removed top layer. And it allows us to see the difference between the external structure and internal structure of this track. For example, see on this photo, we can see that external structure, external topology, it's a smooth layer of nanoparticles. It's a very homogeneous layer. But inside of the track we see random and chaotic topology with many defects, unhomogeneous, with the patterns of melted copper, like here. So different mechanisms generate different topologies. And finally, I'd like to show you our equipment. It's a just standard, say, Supra microscope for scanning electron microscopy. We used it with Gemini electron optics column. And finally, in the end of the presentation, I would like to repeat and remind the main thesis of my report. My thesis is about unique position of LCLD in the group of laser methods. 1 minute, I need 1 minute. In the laser drilling, in the laser cutting, and in the laser etching, we don't use liquid, we use gas. In the laser ablation, we use inert and natural liquid to save nanoparticles, because laser ablation is also a method to create nanoparticles. Okay, in the Zolgal method, we use chemically active liquid, because Zolgal method, it's a chemistry, it's a chemical reaction. LCLD integrates all of these factors, all of these features, because LCLD it's a chemical reaction, and we use in LCLD chemically aqueous liquid, chemically aqueous solution. Also, we need to use, like in Zolgal method, also we use laser to initiate the chemical reaction as a source of energy for this chemical reaction. So laser we use to create the nanoparticles, like in laser ablation. Also, by LCLD, by laser, we create topology in LCLD, like in the drilling, in the cutting, in the etching. And at the same time, we create nanoparticles and conductors. All processes are going on in the same place, in the same time, and LCLD integrates all features. It's an all-in-one method, That's the reason why it's so important to investigate LCLD, laser chemical liquid phase deposition. On this note, on this high note, I'd like to finish my presentation and close this this conversation. Thank you very much for your attention. Thank you very much for your patience. Thank you.